Okay, so I've gotten a lot of questions on lesson number 4, and when I first loaded the video, I think it was Tanush that discovered there was an error. There was a typo that appeared in the video which made the thing confusing. Now I've since gone in, I pulled the MP4 down for that video and back into iMovie, and I've added a banner in there that clarifies that the potential energy of the reactants in this example is greater than the potential energy of the products. And what you're looking at on your screen right now is basically a replica of this problem. So what we're looking at here basically is how energy changes and relates to chemical reactions. And this piggybacks on all of the stuff that we've now done with chemical processes, the last video being the one on the hot zinc. So everything is treated the same for the reactions, but you have to look at things a little bit differently. So in this example, what we're going to do is focus on what happens energetically when we take sodium hydroxide, which you guys have a lot of experience with from the laboratory, and you dissolve it into water. So firstly, when we're dealing with a chemical reaction of some type, this is always going to be the system. All right, and everything else concerning the reaction is going to be the surroundings. So what we're going to do is we're going to place this into a glass of water. All right, and the box that I've drawn on the inside is just a diagram to show the chemical reaction. So I'm going to rewrite it here. We have NaOH that starts as an ionic solid, and then it's going to dissolve into the water to produce sodium ion and hydroxide ion. All right, and if you were holding this glass in your hand when you start this experiment, so you take hold of the glass of water, it's been sitting out at room temperature, which is around, in Fahrenheit, that's around 75 degrees, all right? You would pick it up and you wouldn't feel any real, you wouldn't be like, oh, the glass is hot or cold, right? At room temperature, the glass is going to feel the same as the temperature of the room. Then we add the sodium hydroxide in here, and again, the dissolution of this, the formation of the solution is the reaction that we're following. The liquid surrounding it is the surroundings. And what's going to happen when you add the sodium hydroxide to that, if you were holding the glass in your hand, is you're going to feel it heat up. In fact, it's going to become quite hot. All right, and the reason why that is happening is because as the sodium hydroxide dissolves into the water, energy is actually being released. So I'm going to show that this way. Potential energy is being released, and it's being released in the form of kinetic energy. So out here in the liquid, you're going to see an increase in energy. So we can write the same thing for kinetic energy here. Because what's happening as the bonds of the NaOH get broken, all right, the two products here are at a lower potential energy than the reactants. And the difference in that energy, the difference in the potential energy, is released as kinetic energy. So the kinetic energy and therefore the potential energy of the surroundings is increasing. How do you know this? Because you're holding this cup of water in your hand and you're actually feeling it get hot. So the reason that that's happening is because the temperature is rising. It's going up. And in fact, in real life, if you add enough sodium hydroxide to a small enough amount of liquid, you can actually get the combined surroundings and system to come to a boil. So remember from the past video, right, that our universe is the combination of both these things. It's the system plus the surroundings. And I'm just going to abbreviate surrounding here like that. Right? It's the combination of these two things. And since the system is decreasing in potential energy as it reacts, in order to maintain constant energy, the surroundings is going to have to gain in energy, right? So that's why the kinetic energy is going to go up. And where is that coming from? It's the difference in potential energy between where we start with the reactants and where we end with the products. So for example, if I was just going to roughly graph this, which we're going to be doing soon anyway, and I put potential energy over here, and it can be represented a few ways. I could just call it E if you want. All right, the NaOH is going to start. I'm just going to make an arbitrary place for it, right? And when the reaction's over with, the potential energy of the products are lower than the potential energy of the reactants that we started with. So we draw the line down here, and if I bring this over, you can see that it's at a lower place. You know what, let me try to be consistent, but you guys are going to have to get used to being able to go between PE, KE, and energy. But for now, I'll write it this way. So this is going to be PE2, or PE of the products, and this is PE1. And you can see that PE1 is greater than PE2, and this is where I made a mistake last time on that video that I clarified with a banner. All right, now you might be wondering, what's he mean by the kinetic energy? All right, look at the difference here between these two platforms, right? If we put a number down here by PE2 and we put a number here by PE1, we could determine exactly the energy difference between these two locations. Right? And if you're wondering, okay, so what happened with this gap of energy? This is the KE, whoops. This is the KE in the surroundings. That's what happened to it. Right? This is KE of surroundings. This is why the temperature goes up. YT goes up. This is the reason, because there's an energy difference between where we started and where we finished, and that energy difference, remember, and this was a couple of videos again, that the energy total is equal to the sum of the kinetic energy plus the potential energy. So this energy difference between these two platforms, that is the kinetic energy that moved into the surroundings, and it is the reason why the temperature went up. All right, for this process, for the system, all right, just to piggyback on this stuff, this is what we call an exothermic reaction. And exothermic reactions have reactants that are always higher in potential energy than the products. And exothermic means that the energy moved from the system to the surroundings. So out here in the surroundings, this process was endothermic for the surroundings. Again, think about it, right? The temperature went up. How does that happen? Can't happen unless energy actually moved from the system into the surroundings, and that is an input of kinetic energy. And because of the input of kinetic energy, the temperature went up. And that's the reason why when you're holding a glass in your hand where this reaction is going on, you feel that the glass actually get hot. All right, with that, I'm going to conclude the video. I'm going to upload it and get it into iMovie, and I will provide a link to you a little bit later.